So let's get started. So welcome back, everyone. We're going to be talking about k-means clustering today, one of the classic algorithms and all of data analysis. We'll be talking about Lloyd's algorithm for k-means clustering. And so before we get started, as usual, we'll start by looking at the schedule. We are rounding into the end of the semester. So let's see. So probably on most of your mind, homework 4 is due today. Hopefully everyone's on top of turning that in. It's I guess it's past the point where I can tell you to start early on that one. Please try and turn this in by the end of the day. So I sent a note on Canvas. So hopefully everyone saw it. If you're not getting messages on Canvas, you should make sure you are. But we so over the weekend we finally posted the grades for homework 3 and also quiz 4 and quiz 5. All this just happened to get done so over the same weekend. Quiz 5 was a tough quiz. There's part of this, there was a snafu with Canvas where it did not save the latest updates we had. So a few of the questions were kind of hard to understand, and we gave back points on these questions. But question 4, which was about understanding like projections and stuff, that I think was a fair question, and still people had some challenge with it. It wasn't enough that I think it's going to kind of destroy anyone's grades. So we're not going to kind of change anything about it, but expect to see something like that on the final. Okay. So let's see, and a couple of things. Some of you did not turn in homework 3, or so some people haven't turned in one of the homeworks. Just a reminder, you get to drop a homework, but only if you turn all the homeworks in. If you didn't turn it in on time, you can still drop it, but you have to turn it in at some point during the semester, right? I want everyone to do all the homeworks in order to take advantage of this. The good news is I think you're probably, once you get homework 4 done today, that's probably kind of the most challenging stretch of the course. I think there are going to be kind of some new important stuff happening within clustering and classification, but from the implementation side, it won't be as new or challenging if I ask you to implement anything at all in homework 5, we're kind of finalizing that. And kind of the ideas are kind of building on ideas we've already seen in class. There's not kind of these whole new concepts that I think students have found as challenging in the past. There's some new ideas, but I think you're past the most challenging part, so that's great. Okay, and then we're gonna do this week. We're gonna work on talking about clustering. There's a lot more in clustering we won't cover, but we're going to cover kind of a couple of the very central parts of clustering, as kind of this is an introductory course. We can't cover everything here. And that's the same in all of these areas. And then we'll move on to classification. That will be the last section. There'll be no class on Thursday next week because of Thanksgiving. I want to mention something about the final. Just get some thoughts from you in attendance on this or on Zoom. Feel free to chime in. It is scheduled on. We were given a schedule on the last. I think the last time we can have finals on the Friday, December 17th. So it's on 10:30 to 12:30 p.m. So 12:30 in the morning, 10:30 in the morning to 12:30 after lunch. My plan is to do this as a Canvas quiz again. But it'll be about 4 times as large as one of the quizzes. So very similar format, just 4 times as much. And I'll give you a time window to do that, and you'll have 2 hours to take it once it starts, right? Typically, I start it right at the exam time, and then I let it go sort of later. But this is kind of the end of exam week and into Friday. If that works for you, I can do that. Otherwise, I could start it like, I like to give people a chance in the evening. Some people have kids they have to put to bed or something. Would starting Thursday evening be better, or starting Friday at the time and letting go into Friday evening? So who likes Thursday evening start? Oh, yeah, question first. Well, I would probably end it, it'll at least go through the stated time. It'll probably go for Friday in the kind of early afternoon. Yeah, but I wouldn't go until Friday night. Yeah, so who wants, okay, so Thursday start, let's see, hands again. Okay, versus starting then and going into Friday evening. Okay, and looks like a little, and some advantage for Thursday in the chat as well. So I will probably lean towards a Thursday start. It will include this time, so you can always take it on the scheduled time, and we'll end probably in the Friday afternoon. So those details will kind of come out. Some people have been asking me about the planning of it already. So that's probably going to be the plan. So great. All right. Any other questions about the schedule? Yep.
Just to confirm, the final exam will be online.
Yeah. The final exam will be online. I'll just do it. It'll be, again, it's going to be a lot like the quizzes. You get 4 times as long, so it'll be about 4 times as many questions. We'll have about 6 real quizzes plus the practice quiz, right? So it's going to be not quite cover as much as the sum of all 6 quizzes, right? So think about a little bit less from each topic, but it'll try and cover the whole semester and span what I think are the most important parts.
On that final exam, do you still get like bonus points for submitting like a study sheet?
Yeah, I will do something like that. I'll figure out exactly how I'm going to do it. Yeah, but that seems to be working well.
Should we expect the difficulty to be similar to the quizzes since it's 4 times the length of the quizzes?
Yeah, so the main difference is going to be in the length, not in the difficulty. So it'll be the same sorts of questions I'm asking on the quizzes, right? So you kind of will have some experience with this, and it will be kind of the same sort of difficulty. Now, you won't just have 2 weeks of stuff to keep in your mind at once. You'll have a whole semester of stuff, and I know that makes it a little bit more challenging. But hopefully, some of the earlier stuff, now that you've seen it in action, will actually be even kind of easier and more natural, actually. So yeah, so it's worth, all the quizzes together worth 20% of your grade. The finals worth 20% of your grade. So it's, it's important to do well on, but yeah. Great. All right, so let's get into the lecture. All right, so we're talking about clustering, and in particular, we were looking at assignment-based clustering. As I had mentioned on Thursday, clustering is extremely broad, and kind of the notions of what you're trying to do with it is kind of more vague than these other parts of the course. And assignment-based clustering it kind of specifies things a bit more. Okay, our input is going to be a set of X in RD. At least, again, it can be more general than being like these high dimensional vectors, right? Or two-dimensional vectors, but in this lecture, we're going to focus on it being in RD, and we're given a distance, which is a distance from it can take from RD to RD to R, right? So some sort of distance. Sometimes this has to be, it's like a metric. Some clusterings need this to be a metric. If you don't, I think we talked about what it was to be a metric. Particular, we're going to talk about the case where for two data points, call them X and P, then the distance is exactly equal to the Euclidean distance. Okay, we're going to look at the Euclidean distance here in this case. Okay, and now the goal is going to be a set of sites. We'll call this set S, and we'll label them in class notes with C's because lowercase s's look too much like uppercase s's. CK will be, so far we'll be given K as input. Value K, right? So the K is given as input here. We'll talk later in this lecture about if you don't know what the value K is a bit later, but we're trying to find a set of these sites. These sites will be a subset of RD also. Okay, these will be the representative of the clusters. Okay, and we would like to minimize, some function which goes over all X and X of somehow the distance from X, each one of the data points, right, are X is equal to X1, X2 up to Xn, right, to the mapping onto the set of these sites from X to the closest point. Okay, so I'm getting some function of the distance from X to its closest point here. Again, okay, we'll think about these are the points X. Okay, let's say K equals 3, and I'm going to get these sites, right? So this will be C1, C2, and C3, and I'm going to basically assign every point to its closest of the sites. Could be like a center or a mean. They're called different things, so I'll just call it a site. I'm assigning everything, right? So this function here, phi, this is key. It maps X to the closest CJ in S, right? So it maps this to its closest point. So this is like our projection that we used in dimensionality reduction, except it's not onto a linear subspace. We don't have the niceness of dot products to help us define this. We have to find the closest point and map it onto the closest of these sites, right? We want to minimize some function of these green costs, right? Each of these these green lengths here, these correspond with the distance, right? That's the cost of the mapping. That's like the residual, right? So the residual, and there are different functions we can have here. Okay, the most common function right? So is to minimize X of all these sites, to look at X minus phi of S of X squared, to minimize the sum of the squared residuals, the sum of the squared errors. This is the most common. This one is called K means costs, and that's what we're going to be talking about today. There are other ones which are also studied. X and X. Okay, this is non-squared, so I don't square the cost, right? What if I just minimize the sum of the distances? This seems maybe more natural. This would be called K, the K median problem, right? This is the K median problem instead of K means. If I'm in one dimensions, it turns out I will take a median at a point instead of a mean, right, to solve this one, and that's kind of why it's called the K median. And then there's one called the K center, which is the max. This is called the K, the K center. I just care about the maximum distance. So I want none of these green edges over here to be very long. I want to minimize the longest edge. All right. And each of these has slightly different algorithms of how to solve them. In fact, there are multiple algorithms for each of these kind of these problems. Okay, and so these are the most common variants here. I'll mention there's a version of this K median called the K medioid, where this must be that S is a subset of X. Okay, if I restrict that the centers or the sites have to be data points, then the K median is called the K medioid. It turns out that if you want something that's going to be robust to noise, the K median is kind of the most logical thing to use. The K center, it only cares about the largest point. So if you have one point which is noisy, then that one point is going to cause the cost function, and the rest of what you do doesn't really matter. So it doesn't really help if you deal with noise. A lot of the answers it gives is not very helpful. It just cares about that one noisy point and how to capture that. The K means looks at the distance to all the points, and if there's an outlier, well, it squares that distance, so that distance becomes more important. And so this is the K means is more sensitive to outliers than the K median. Okay, but the K median is going to be not going to have as nice of an algorithm. We'll see. We'll talk about K means. It's going to have a pretty nice algorithm towards solving it, and that doesn't quite work as well for the K median algorithm. Okay, so that's why K means is typically more popular. But if you were to restrict that the solution had to be one of the data points, well, then that actually means I don't have to search all of RD, all the d-dimensional space for the choice of the sites. I can just check the different data points. And if I'm going to do that, well, this optimization function is a bit better. It's a bit more robust to noise, and this might be a little bit better to use. So K medioid is the version where they restrict to the set of the data points as the sites. Okay, so that's kind of the main story with the variance here. You could think of other variants. I could minimize the sum of the cube distances if I wanted to, right? That one doesn't have a special name to it, at least not that I know of. But you could imagine other versions of these. Okay. All right, so we're going to talk about, again, the K means version. That's going to be the focus for today. Okay, there's a really cool algorithm for K center algorithm that's in the book, but we're not going to get to that. Okay. All right, yeah, oh, chat. Let's look at the chat. Oh, is that phi or another? Yeah, okay, good. Hopefully you. Yeah, so these are, the phi is the mapping onto there. The d is the distance. I will drop using the d. It's a little confusing. It's also the dimensionality here. So I'll just use the symbol for the Euclidean distance in this case. These other ones don't necessarily need the Euclidean distance, but the k-means will need it to be the Euclidean distance as the focus today. We will restrict to this sort of setting. All right, let me actually, before we talk about an algorithm, maybe I'll just show you kind of a demo in Python. Just like a lot of the stuff is built in, I'm going to show you kind of a nice example of how you can run this. We're going to describe the algorithm. It'll be intuitive. You'll see it's easy to describe in the simple form. But then to make it work, there are kind of a lot of little details you want to worry about. And so I'm actually not going to have you implement this algorithm yourself because of that. So we'll talk about some of these issues. Let's start by, so I'm going to use one of the most common libraries for data analysis within Python called sklearn. Okay, and sklearn has built into it this nice function where it makes these kind of blobs, these nice clusters. These are kind of imagine what you would think a cluster might look like. And on Thursday, we'll actually talk a little bit about what it's doing when it's generating these clusters and how we can leverage that to have a little bit better model. But okay, I'm told to create 100 points with 4 centers, standard deviation 1, and I chose this random state 6 because that makes the picture nice. It does it at random, and some of the other initializations weren't quite as nice. Okay, and basically I can run sklearn. I say I want to run k-means with 4 clusters, and then I give it the data set X that I generated, and it does a fit, and then I can predict, I can map everything onto labels. These labels I can then use to color the points. So that's what I'm going to do here. It does it, I did this automatically. This is pretty opaque what's actually going on, but the result is these 100 points, I've colored them green, blue, yellow, or purple, and at the red sites or the centers, whatever, are the big red dots in the middle, right? This is my goal. I want to identify these red dots and it assigns all the data points onto them, and they're drawn in colors here instead of the lines I drew earlier. Okay, so this is our goal. We're going to explain basically how this works, how we're going to find these red points to do this sort of assignment. All right, so that's what we're going to do. We're going to talk about basically how this algorithm that it's, if you read this, it's not even clear where it's actually running the algorithm. It's in this fit line here, actually. But, how that is actually doing. And we're going to, explain what is going on inside this black box. Okay. All right, so yeah, so our goal here again is going to be looking at a cost function, cost that balances X and the set of the sites, and we're going to write this as X and X of mapping X onto the closest of the sites. And we also talked about last week how the set of the sites, C1, C2, C3, and C4 gives rise to this so-called Voronoi diagram, which kind of tells you how to divide the space up. And we're going to kind of see this picture kind of in action to kind of explain. This will tell you how the mapping actually works. So now if I have a data point here, I know it's in this region, so it maps onto C C2 in this case, because it's in the region defined by those blue lines. And that function is going to be kind of, in 2D, you can compute it. There are algorithms that's well studied, but in practice, we're just going to check the distance. We're going to, for each x, I'm just going to compute the distance to all of these, right? And figure out whichever one is the shortest and say that one's the shortest, I'm going to use that one. So, all right. So, okay. So, and what we're going to talk about to do this is called, so Lloyd's algorithm. Okay, there are a number of algorithms. This one was this researcher, so Stuart Lloyd, and working at IBM Research in like the 1950s, came up with this algorithm and then never got around to publishing until 1982. But it's really his algorithm. He was quantizing stuff only in one dimension when he came up with this, but it generalized nicely to any sort of dimension. Okay, and the algorithm is going to be kind of like a gradient descent sort of algorithm, but we're not computing the gradient, all right? Kind of like the power method didn't explicitly compute the gradient, but it got closer and closer to the first eigenvector. We're going to do something similar here. It's one of these so sort of iterative algorithms. In order to define this, I want to have a little bit of notation here, and I'm going to say that xj is going to be the subset of all of the data points such that if I look at the mapping onto the centers at x, it's equal to center j. Okay, so this is the subset of the points. So this set of points over here, right? These guys, all these points are going to be x2 because they map onto the center 2. They're a subset of the data points which map onto the second center. This notation will make kind of describing stuff a little bit easier here. Again, given the set of sites, we can compute which data points map onto it. Okay, but we don't know where to place the sites. And so when you change where the sites are, you change which points are mapping onto those sites, right? So it's kind of like this chicken and egg problem. Okay, and all right, so now I think I can write down the algorithm. Okay, so step one, I'm going to, so initialize this. I'm going to choose k points, and typically you do s as a subset of x. Okay, I'm going to choose k points as my sites, which are a subset of the original data points. It doesn't have to be a subset, but this is typically how you would do it. And as we change it, they're not going to stay a subset. Okay, they don't need to be a subset initially, and I'll come back to how we actually do this initial choosing. But the first point, it can be arbitrary. I've chosen some subset, and then I'm going to have a repeat step, and I'm going to repeat until some condition is reached. Okay, and 1a. There are going to be two steps I'm going to iterate over. Not like gradient descent, I only had one step. I'm going to have two things I need to worry about. The first step is for all x in x, I'm going to assign x to xj such that phi of s of x equals cj. Right, so I'm going to do this assignment. I'm going to create these sets. Okay, they're defined mathematically, but the algorithm may not know what those sets are. So I'm going to create these sets, right? So if I want to create these guys, that's happening in this first step here. This is 1A. Okay, so the second step, 1B, is going to be, well, okay, once I have the sets, then I can assign so a site. Like, in order to do this, I needed to have the sites in order to assign the sets. But now that I have the sets, I can say, well, given all the points in the green blob, I can choose maybe a better place for the site corresponding with these points, right? So for all CJ in the sites, I'm going to update CJ to be equal to, well, what is the average of all the points which are mapped onto it. Okay, so I'm going to update the site to the mean, that's why it's called k-means, to the average, the mean of all these data points. All right, so if I'm choosing a new update, you know, this would be CJ prime. I've updated it to be the average of all the points in that set. It's these two steps, right? And so after that, then the assignment may change, right? Which point maps to what center may change because I've assigned where those sites are. And so I'm just going to have an until so like there's some sort of condition, either R rounds or the sets XJ so changed. Okay, so either I'm going to say I'm going to go for 20 rounds, 20 loops of this, or I'm going to say, well, I'll stop if I'm not updating the location of the assignment for any of the points. If none of the assignments changes, well, then I can also stop. That means, well, if the assignment didn't change, then when I do the update, I'm going to get back exactly the same set of sites. So I'm going to get the same assignment. So I'm not going to change anymore. So I'm going to stop. Right. So this is the whole algorithm. Yeah. So to return S. Right. So return this set of the sites. Right. So that's my answer. That's my representation. Okay, so I'm going to iterate between mapping every point to the closest site and for each site, taking the average of all the points which are assigned to it. All right, so let's try and go through an example. Hopefully this will kind of clarify what's going on here. Okay, hopefully, I mean, the two steps should be pretty simple and straightforward. Let's go through an example with k equals to 4, and I'm going to try and draw an interesting case here. All right, so this is my data set X. Okay, and let's say my initial set of the sites. Okay, k equals 4. My initial sites, let's call this S1, S2, S3, and let's do S4. Okay, so these are some initial set of sites I've chosen. These are not the optimal ones. Okay, yeah.
Can you clarify the difference between sets and sites?
Yeah, so okay, the sites, right? These points, the initial points, S equals C1 up to CK, which is going to be a subset of RD, these are going to be the sites. Okay, these are going to be the sites. These are like the centers of the cluster. These are the red points here, right? The red points up there were the sets. These guys are the sets. Okay, so that's the assignment of us. I'm breaking the whole data set X, big X, down into these subsets, Xj. Right? Each subset Xj is a cluster of the points. Right? The one of the goals here is kind of a simpler representation of the data. Right? So if I just return all the points, but with labels on them, that's okay. That's not really a simple representation. If I just say, I just going to return these k, in this case, 4 points, then I say that represents the data. Maybe I could say, C2 has 6 points assigned to it. C1 has 4 points assigned to it. It gives me some intuition of where the data is located in a compact form. And that's what the sites give me. The sets are the assignment. Right. Great. So yeah, so 1A is updating the sets, right? This is update the sets, and this one is update the sites. Is 1B is updating the sites. Okay. Great. Okay, so I have this example. I've chosen the 4 sites here, and now I want to define the sets associated with these points, right? So, and I'm going to do this represent this by drawing the Voronoi diagram, right, which kind of tells me how these are how these are kind of the boundaries in between these points. Okay, so I'm kind of getting the boundaries in between these points here, and so now this implicitly defines the sets, right? Everything in the bottom left corner by S3 is assigned to set X3. Okay, everything in the upper left corner by S1 is assigned to S1, right? So this is all S1, this is all, X1, this is all X3. X2 is only a single point, right? And X4 has this logical set, but also from this kind of grouping down here, right? So this does not seem like the right answer. This was my initial guess, okay? And so now the first set, the first step here, I'm going to kind of think of drawing the Voronoi diagram as representing this assignment, okay? And then I'm going to this 1B, I'm then going to optimize that assignment. I'm going to optimize the placement of the sites, okay? So I'm going to S1 is going to be moving to the center of all of its points, right? All the points in this region here, I'm going to kind of, that's going to be, I'm going to optimize the center to S1 to this red point. Okay, S1 is going to move here. S2 is not going to change. It only has a single point in its set. So it's not moving anywhere. Okay, S4, what's going to happen with well, let's do S3 first. This is more intuitive. S3 is going to move down here. It's kind of the average of all this kind of grouping down here and this one straight point in the middle. Okay, and S4, now it's got 2 groups of points. Actually, let's say that this one point on the boundary was part of S3. This will make it a little bit more interesting. That's going to move S3 towards over here because it's drawing on this point over here as well. Okay. Now S4 has most of that set of points, so it's going to be kind of in the middle down here. S4 is going to be here. It's kind of splitting the difference. Okay. Okay. So let's see if this is any better. Let's redraw the Voronoi diagram between these, right? So let's say that now S1 and S2 still basically has, combinatorially, it's about the same division of the points, but it's shifted a little bit. And S3 and S1 now are going to go here. Let's make it a little bit more interesting and say it goes like this, right? S3 and S4, maybe this is shifted slightly. And let's see, S2 and S3, so I need to up this a little bit, and S3 and S4. Okay, so I've kind of moved here just a little bit. I've tried to make it so it's not working quite as well as it could, just to show a few more steps. Okay, now S2 is still in the same spot. All right, S1 is going to be moving down here a little bit because it now has this other data point. S3 is going to be moving down here, and S4 is actually going to move back up this way. Okay, maybe I made this work less well than I should have. This one might not. Okay, let's say S3 move back here. Okay, this is not great. Okay, so let's say it looked like this and erase here. You do these examples. Okay, online like this, they might not turn out perfectly. Okay, so now let's do one more iteration of this. S3 now finally is moving to a good home. S1 is now over here. I want S4 to now move down back this way, and S2 is still here. What I'm hoping will happen is that this is going to cause some of, let's say, S2 is able to now, because S4 shifted down, S2 is now going to grab some of these and eventually will move over to this cluster. Okay. And so now it's finally going to move over here. Luckily, I've got lots of colors in my palette. All of a sudden, S2 is going to move over here. I missed an edge here. Okay, now S4 is going to move down here. This will be S3, and this will be S1. We'll actually get this other point, and we'll end up getting a diagram that looks kind of like that. And now everything is kind of in the right zone, right? So now I'm kind of finally getting, this is associated with S. This is now the set X1. This is now the set X2. This is now the set X4. And this is the set X3 after these iterations. Okay, so as I shift the centers, it updates the partitioning of the sets. And when I update the partitioning of the sets, then I can re-optimize the centers. And hopefully they gravitate, as soon as S2 got kind of part of the mass from over here, then it really shifted over here, and that kind of situated everything the right way. Okay, so, okay, hopefully that gives you a little bit of a taste of how this is working. Okay, any kind of questions about this, the structure of how this works? And yep.
So minus the labels, we'll always get those clusters, no matter where you start.
No, that is unfortunately not the case. Okay. Yeah, the algorithm is very simple in that the two steps are I just reassign to the closest point, I take the average, but it's not guaranteed to always work and always get the right assignment. Yeah, that's a great question. In fact, let me show I tried to make that a little bit too tricky, but let me give an example where right, so let's say I've got a bunch of points over here, and I've got, okay, so if I have k equals to 3, and I pick two sites, S1 and S2 and S3, what's going to happen is I'm going to basically divide. Yeah, so I'm going to divide the space up like this, and on these two sites are always going to be stuck over here, even though it's going to be better if I move one of them over onto the right hand side, right? So I'm not always going to be able to get over there, and it's going to get stuck. It's like a local minimum, right? So I'm stuck in a local minimum here, and the algorithm won't always converge to the right answer. This is unlike things like with regression when we had a convex function, or with the power method where by kind of the magic of the stretching, it basically always converges to the right answer. That's not the case here for clustering. Clustering is a much harder problem, and there could be a lot of these local minimum that it gets stuck, right? And it could be, kind of arbitrarily bad. You could think of stretching them further and make those two sets that S3 is trying to capture even kind of more separated from each other, so that one point is not doing as well. Yeah.
So when you choose your initial guess, you want to look at the data intentionally.
Yeah, so if you can do that, that would be great, right? What this is really good at is optimizing the clusters once you've identified the right sets, optimizing the sites once you've identified the right sets. And it does fairly well. Like even in this example, eventually S2 wandered over to capture, right? In a lot of cases, it will do that. If the clusters are kind of well formed and they really are distinct, a lot of cases it will actually work out, but not always. So great question. So so let me write this up here so it's concrete. Does not always converge to the optimal solution. Okay, so it's not always going to it can get stuck like this. This is a local minimum. Okay, so a question is, so a point is the initialization is so important. Okay, so the initialization, how I initialize is going to be fairly important. So you would like to get goal is one site in each kind of true so cluster, right? I would like to get one site in each true cluster. If I get this, it should work quite well. Then it should really optimize probably to the optimal solution. Okay. So what are some ideas all of you have on how I should try and initialize the points? Yep.
Pick them yourself.
What?
Pick them yourself.
Okay. So, all right. So if I have points, right, and I can draw a picture, I can plot them, right? I can plot them. Well, I say, well, now I can draw this picture and I can choose the sites and then the algorithm will optimize them for me. Okay, good. So one option, kind of plot, choose, and then so optimize, right? The algorithm is good at optimizing, but it's not necessarily good at initializing here. Okay, so this works. I can plot if I'm in low dimensions, right? If I'm in 2D, I can plot it. This is powerful when I'm not, again, if I'm in 2 dimensions, all I care about is the actual clusters, and I can just draw circles around them. And that's gonna be as good as just about anything else. So if I'm in higher dimensions, am I able to do this? Well, I could maybe run, I could run PCA first, down to 2D, and then plot it, and then try, and that's not necessarily a kind of a bad thing to try and do. You might get 2 clusters on top of each other, but PCA kind of tries to avoid that sort of thing. So yeah, that's actually a reasonable option. That's probably not as common of an option as it should be among people. I don't want to tell you not to do this. It's probably a good thing to do. If it works, great. If this doesn't work because I'm in too high of a dimension or something else, what else can I do?
Yeah. Could you potentially look at the distance between points and make sure that it's past a certain point?
Oh, okay. So ensure, yeah, so option 2. Option 2, ensure all kind of distances SI, SJ, or these are between the sites. So you see CI, CJ, CJ prime is large, right? So I want to make sure the sites, an issue here in this initialization is site 1 and site 2 are too close to each other. Kind of, and this caused problems. That also seems an issue here. Site 1 and site 2 are too close to each other. Although if I picked site 2 to be down here, it would have been pretty close to site 3, and that would have been fine. But yeah, so this is a good thing. I'd like to ensure that the sites are far from each other. Actually, this is basically there's an algorithm called Gonzalez algorithm. Okay, that basically tries to enforce this. And this is, we're not going to cover this in the class, but it basically picks the first site anywhere, then picks the second site to be the point that's as far as possible from the first site. The third site, the farthest possible from the first 2 sites, and iterates this. And this actually is good for k-center clustering. And it's a decent way to initialize here. And there's another option called, that's actually a bit better, called k-means plus, that actually does this in kind of a randomized way. That picks them probabilistically far away. This is less likely to get selected by outliers. Okay, so this tries to choose them pretty far away from each other. And actually, the k-means plus, you can actually prove some things about that. It won't always work, but it'll sometimes work. So it'll sometimes always work. It will always sometimes work, which means that for any data set, if I run it, it's a randomized algorithm, sometimes that will give me a good initialization. So if I run it enough times, I think maybe like 8 times, one of them will be good, and so I can try all of them. Okay, so this kind of gets to a simpler option, which I'm just going to kind of recommend for this class because we're not really going to go into these. And this is just going to be so random. Okay, so I'm just going to choose S at random. Okay, so I'm just going to choose the initial set of sites at random. This will not always sometimes work. There are some data sets where this will, with high probability, not give you the right solution. They're kind of weird data sets that are not very common. And as the number of sites you need gets really, really big, if K is like, 10% of N, then this gets hard to hit all the points, right? But if K is small, if K is 4, and then eventually this will probably work. And so this is just kind of a concrete suggestion. Now, that means it will probably work eventually, which means I need to actually do this with this idea of random so restarts, okay? And the idea is, set kind of the best score I have. Let's call this best score equals so infinity, and say for, let's say t steps. Okay, I'm going to do a random, so init, I'm going to then run Lloyd's, let's say this is S1 on, right, so on, okay, x comma s, or s j, right, so j equals 1 up to t, right, and then I'm going to get score, or I'm going to get if the cost, right, this is the sum of the squared cost of x sj, this is the output of the algorithm, is less than, or is less than best score, then I'm going to say s star equals sj star, and best score is equals to this cost I've got here. Right, and so, and then at the end of this, I'm going to return S star, right? So I'm gonna do random restarts, okay? So I'm gonna randomly initialize, and this can be with k-means plus plus or just a random sampling. Run Lloyd's algorithm on that initialization. If the cost is the best so far, then this is the best so far. I keep track of it. And then I return whichever is the best. This random restarts gets you out of a lot of kind of trouble. And usually this will work pretty well. So often you will run Lloyd's algorithm and it might not work, but you run it a few times and one of those will probably work pretty well. Okay, so this is kind of the common thing. There's one more option. Okay, I want to say is I'm going to kind of use a large K, right? So let's say K prime equals, say, 10 times K, then merge. Okay, so another common option is I'm going to run the algorithm with a much larger value of K with more sites, right? If I were to run on this case with more sites, let's say I ran with 6 or 7 sites, and I say I initialize random, I'm more likely to get at least one site in each of the kind of the 3 clusters. Once I have the 3 clusters, then I can kind of figure out how to merge these clusters afterwards. These 2 points, if I combine these together, it's not going to increase the cost too much, and I can get back to my original K. So that's another approach, and this actually works fairly well, especially when your K is already fairly large. You're trying to find a lot of clusters. It might be hard to hit all the pieces in a random sample. There's this thing called like the coupon collectors problem. Has anyone heard of this? Where like the idea is you have like you're going to McDonald's and they have like Monopoly Week, right? And you want to get all the properties, and then you get a Monopoly and you get this big bonus prize. And so you have to get each of them, or if you want to get all the toys at McDonald's, and so you have to get a Happy Meal, until sometimes you get one you've seen before, right? So how many do you need to get until you get all the toys? Well, if there are K toys, you need about K log K Happy Meals to get all the toys, right? You need an extra log factor. So you give an extra log factor of initial points, so not factor 10, but maybe this is K log K. Then I'm probably going to hit all of the different spots, and then I can merge them back together again. Right. So this is another pretty good option. Again, this is why I mentioned the algorithm itself is kind of nice and cute and fairly short. But this is kind of one of the issues, right? It might not converge to the optimal thing. So there are lots of these kind of strategies for trying to initialize them. K-means plus and random restarts is built into a lot of these packages now. Although K-means algorithm was like in 1957, K-means plus came out in just 15 years ago or something. I remember actually a couple of when I was in grad school, a couple of my friends who were in grad school someplace else actually came up with this algorithm, and this was kind of the people. So that was one of the things I wished I had come up with, right? I was working on things at that time, and someone else got that great idea. Okay, so this is one of the issues. There are a couple of other sort of let me mention a couple of other weird things that might happen. As you're running the algorithm, I might get, let me show you another weird thing that can happen. Okay, so let's say I start kind of here in this sort of setting, and okay, this is kind of my Voronoi diagram, and I update to here, right, so this guy goes to here, and this guy stays here. But after this update, if I've drawn this correctly, something weird can happen. Okay, and what's going to happen is if I look at the setting, these points are assigned to this blue point over here, right? These points are assigned to that blue point, right? These points are assigned to this one. And what's going to happen with this guy right here? Which points are assigned to it? What is the set, right? So if this is, say, let's call this guy S2, X2, is all of the X in X such that phi of S of X equals S2. What is the set X2 here? So it's empty, right? No points. This algorithm was such that no points are assigned to this site. And this can happen, especially if you have a lot of sites you're running this with, this will happen. And so if I try and compute an average, I'm dividing by 0 because I'm dividing by the number of points in the set. And so I have to do something strange in this case as well, right? This is one of these other weird cases you have to deal with if you're implementing this. And typically what I would do is I would do a random kind of, I would set S2 as a random X in X, right? So I would choose a random point in the data set and reassign S2. That's a common thing. But again, there are these little weird details that show up here, right? So it's kind of there's some messy details in the algorithm, even though the algorithm itself is kind of simple and intuitive. Okay. Okay, let's see. Great. I want to say a little bit about the convergence, though. Okay, there are some nice things you can say about the convergence of Lloyd's algorithm, and this is really why kind of people are commonly. Actually, let me move this down here. Okay, this is really the reason why it is quite common to use. Remember that the cost function is x minus phi of s of x squared. So I can write down this compact kind of cost function here, right? Using this phi to make this notation concise. And this is one way of thinking about it. Another way is writing it explicitly using the sets, right? So for each Cj in this set of sets, I can actually write the sum over all x in xj. This is the corresponding set, right? Remember that all the points map to the same site. And then I can just write Cj minus x. All right, so this is an equivalent way of writing this down. Okay, and this is, so I can think of these two different ways of writing the cost. And what's nice about this is that now when I'm thinking about the Lloyd's algorithm, I have 1a where I'm kind of going to optimize xj is equal to, or I'm explicitly computing xj, so I'm reassigning points to different sites. Right, so I'm optimizing this, I'm reassigning the points to the sites, and then 1b, I'm going to, so 1a is optimizing the sets, this one is optimizing the actual sites, right? So I'm not using any implicit definition of phi of s here. I'm using it explicitly, right? So this is optimizing the sites. Well, okay, so if I look at 1a, right? So if I'm looking at 1a here, this optimization, well, that's exactly what's going on here. I'm choosing the optimal, the closest site in the first plot, in the first view of the cost. So I'm definitely decreasing the cost function when I'm doing this, right? When I'm doing 1a, I'm mapping every point to the closest site. So this cost function has to be going up, right? And if I look at 1b, right, this, if I'm optimizing the location of the sites, but I'm fixing this fixes, right? I'm fixing xj. This is not kind of implicit with kind of this phi of s. Okay, so I'm not implicitly defining it, I'm explicitly saying this is the these are the sets I'm working with, right? Well, then I can look at these terms individually, right? I'm not changing what the sets are. So I look at this internal blue region, and then that costs the choice of Cj, right? I can argue that this is the optimal solution for this step. Okay, and this is what makes the algorithm nice. Both steps are decreasing the cost. And I'll go through this argument a little bit more detailed, what the algebra is. But if you can argue that this way of setting the center is the optimal placement of the site for this set of points in the corresponding set, then that's also decreasing the same cost function. So that means that every iteration, either 1a or 1b, I'm decreasing the overall cost, which means that I can't go back to an old configuration I'd seen before, because if I had done that, then the cost would be higher, but I must always be decreasing the cost. So this will converge to a local minimum, but it might not be the global minimum. Okay, so it can at least do that. Yeah, so the default, oh, great. I missed that comment before. Okay, great. Okay, so this algorithm makes it very easy to optimize, and it's because the sum of squared cost functions, the sum of squared errors, it has taking the average is what gives me the optimal cost, given I've identified that set. Okay. Okay, and we've kind of made this argument before. We've made the argument early on in the semester that in one. Okay, yeah, great. There's some more details in the chat on different various other ways you can optimize k-means. Okay, so there are. Yeah, so we'd argue that if we're in one dimension, that we can actually, that this taking the average is what minimizes the sum of the squared errors. We did this by writing down the cost function in 1D, and we took the derivative and we set the first derivative equal to 0. We said that occurred exactly at the average. Okay. So okay, so we proved for in D equals 1 that the average so minimizes the sum of the squared error, right? That minimize the sum of the squared error in so 1D, and so what's nice in so higher dimensions, that the average does the same thing, right? So I can set kind of a set of points, and remember these have x and y coordinates, and if I choose kind of like a center, well, what I'm doing is I'm looking at this. Yeah, let me just draw this here. Let's just draw this in 2D. Let's say these set of points, right? This set is xj, okay, and I'm going to choose a potential center cj, and if I look at one of these distances, right? This is 1 point x. That this distance I can write as the sum of two parts, right? So I've got the distance on the x coordinate and the distance on the y coordinate. Okay, and okay, so if I this hypotenuse is x minus cj, right? And I care about some, let's call this the distance x and the distance y. And what do I know about this equation? Well, I know the hypotenuse squared is equal to the distance x squared plus the distance y squared. Okay, and because I'm minimizing the sum of the squared errors, that I actually know that x minus cj squared is equal to the distance x squared plus the distance y squared. So if I optimize all that distance on the x coordinates, and I optimize all the distance on the y coordinates, well, I can individually optimize them. I can decompose them into the x and the y coordinates because of the Pythagorean theorem. I can optimize these individually, right? I can optimize independently, okay? I can optimize these independently, and that will optimize the total squared error. And so this is what's nice about the squared error with the Pythagorean theorem. I can optimize the individual components, and that's why when I take the average, I'm doing an average of vectors. This is a vector average which is really just a coordinate-wise average. Each coordinate I'm averaging independently, and that gives me the overall kind of minimizer of the sum of squared errors in Euclidean distance. Okay, so I'm getting an optimum choice of the site given the set in 1B, and that's what really makes this algorithm nice. That I know it's always decreasing the cost function, and step 1B is pretty easy. If I were instead had a sum of just the distances, the k-median formulation, not the sum of the squared distances, I would not get quite as easy as a step 1B. There is a method how to do step 1B, but you can say what's the point that minimizes the sum of the distances. That's a much harder problem, actually. And kind of it itself requires like an iterative solution, more or less. So I can't just have a closed form solution for 1B. So that's why this algorithm is kind of very popular, because I have that step 1B, which is very easy to solve. Okay. All right. Okay, I'll get to your question at the end of the lecture. I want to say one more thing, one more important thing that to cover. And I say how to choose K, right? I said, well, you can choose a larger K and then you can thin it, but kind of this is, you also have this problem that as K goes to N, I get one data point in each cluster is the right solution. And that's not very interesting, right? But my cost function goes down. In fact, one way you can think about this is I can draw K, right? So K equals to 1, K equals to N, and this is going to be the cost of XS, right? Where K is here, right? So the cost function, what's going to happen to this cost function? It's always going to go down, right? And eventually it's going to basically hit 0, right? So I'm actually eventually going to get a zero cost here as K goes to N. So just looking at the cost function, you know, this is not going to tell me how to choose this value of K. Okay. Okay. So this doesn't really help. I want to draw two kind of cartoons of what the cost function can sometimes look like. And one version is going to be often like this. Okay, this is a good kind of situation for subclustering. Okay, and another example would be where it kind of goes like this. Okay, this would be kind of a bad situation for subclustering. Okay, so what the difference here is the red one kind of is the sharp drop and then levels out. The green one kind of is a gradual. And the difference is the green one, the green data will look something like this. If you draw green like this, there aren't really any clusters here. It's kind of this blob or one blob or a smear. And if I do this with the red data, it's gonna actually, this is gonna be from a case where I actually have some number of clusters. And in fact, it actually tells me there is some kind of interesting point here. This point here is called the elbow of the curve. When it drops down and then it starts to level out, this is the elbow, and this is a good choice for K, right? So this would be a good choice for K right where this elbow is occurring, right? Imagine that like you have your arm, I can't get it in the frame, but it drops down and then it flattens out, right? So think of there's someone's shoulder up here, you know, they're smiling because they're in this class, right? And they're having a lot of fun. And then they have a really long arm here, and then it right? This is the fingers, right? And so this is kind of the elbow of their arm where it bends down, and this is how you want to choose K. So it seems weird. You want to run the whole algorithm over and over again with a bunch of different values K. I have to rerun it for each value of K, but then I can give this plot, and if it has a sharp drop and then a plateau, then that's a good place to choose K. Okay, something like this can be used for kind of doing like dimensionality reduction as well. Except then I can just look at the singular values. That captures it for me. The value of the singular value. The first one is very large, and then it drops down, and then sometimes it gets very close to low rank, and then almost zero, right? And so I can do a similar thing there. And this is called the elbow method, and this is kind of probably the best way of choosing K. There are some statistical ways you can use to say, okay, is this cluster different from this other one? How much information am I gaining? These are all based on fairly explicit models and assumptions of what the data looks like. And in some cases, they're great, but they don't always work. If I knew what the data was going to look like ahead of time, I wouldn't need to necessarily run clustering or choose K. Sometimes those are appropriate. But if I don't know anything about my data, then this is going to be is kind of the more helpful, intuitive way of doing it. You can also plot. Again, you can go back to plotting and look and guess, and that's another good way of doing this. Okay, great. We will stop here, and then on Thursday we will talk about mixture of Gaussian's approach, which will seem kind of very complicated, but it will be a simple extension of Lloyd's algorithm, what we'll be doing. And instead of just finding the sites and the centers, we'll actually fit a Gaussian and a kind of a stretched Gaussian onto each of the clusters and give us a much more explicit model. And we'll talk about kind of the extra power you get with that, and we'll maybe kind of address some leftover thoughts you have in your mind. Okay, good luck finishing the homework. Don't forget to turn that in.